If you recall yesterday, we looked at this function of two variables, and we want to find the critical points and classify each critical point. We had a memory check where I gave you a function of one variable, and I said find and classify the critical points. What we did was take the derivative, set it equal to 0, and solve. The first derivative, take the first derivative, set it equal to 0, and solve, find the critical points. Then when we moved up to a function of two variables, we did the same thing. We just have two derivatives to set equal to 0 and solve. So we took the two first partial derivatives, set them equal to 0, and this created a linear system for us to solve. So we have to solve the linear system because we're solving f prime equals 0, although f prime, since we have a function of two variables, is these two first partial derivatives. So the way I chose to solve it is to use a matrix because I had a calculator sitting right next to me. And so I just matrix math, I think it's B. And I just put in each row of the matrix, 4, -3, and I solved for, I put the 1 on the other side to make the augmented matrix. So I'm looking at this linear system. So I'm solving 4x minus 3y equals -1, -3x plus 16y is equal to +1. I thought about solving this system. I realized the horrible mistake that I made having a determinant of my coefficient matrix of 55, and then decided to go with my calculator. So I put the system into a matrix and found the reduced or echelon form of the matrix. So 4, -3, -1 in my first row, and -3, 16, 1 in my second row. And I got x equals these two values. And I converted it to a fraction because it'd be easier to write. So x equals -13 over 55 and y equals 1 over 55. And here is our critical point. That's just solving the system of equations. I happen to use, I use the matrix to solve the system of equations because that was going to be fastest. We could also try canceling out, like make the x coefficients opposite 12s or the y coefficients opposite 48. That's all right. So all we did was solve the system of equations to come up with these values. So I used a matrix to solve the system of equations because that's fast. It's kind of crazy to grab a machine to solve our system of equations when we could just use a slightly more advanced machine to just find the critical points. But the algebra wasn't the important part. I'm confident that if I had to solve the system 4x minus 3y is -1, -3x plus 16y is 1, we'd be able to sort that out. Starting to wonder if like a system like this, Cramer's rule would actually be useful. Crazy thought because I mean, like I hack on Cramer's rule on a regular basis because it seems so crazy. But when you have a system of two equations and two unknowns, and the answer can come out weird. Like I knew both denominators were going to be 55 because we got the 64 minus 9. So I knew it was going to be 55. That's why when I wrote the system down, I'm like, ah, crap, I'm just going to use a machine. But then I could have just dropped the -1 and 1 in here and been like, oh, -16 plus 3. There's the -13. Cramer's rule, I officially apologize. That would have been confusing. Yeah, is anybody familiar with Kramer's rule? All right, since it came up. Oh, I should write things proper. One of the things that you're going to need for Kramer's rule is something that we're familiar with, very little bit, the determinant of a 2x2 matrix. So the determinant of the matrix A, B, C, D, read as rows, sometimes noted just in absolute value signs, is AD minus BC. That's called the determinant of the matrix. So Kramer's rule has the following. Let's suppose that we've got a linear system. AX plus BY equals, let's P, and CX plus DY is equal to Q. Kramer's rule would have you calculate three different determinants. One, the determinant of the coefficient matrix. That's going to be your denominator. So I'm just going to write the determinants. So Kramer's rule is a way to solve this system just by calculating determinants. Let's preface it that way. So here's how to find X. X is going to be the ratio of a couple of determinants. In the denominator, you're going to do the determinant of the coefficient matrix. Spelled C wrong. In the numerator, you're going to replace the X column with the constants and then calculate the determinant. To get Y, you do the same thing, only put the constants in the Y column. PQBD, because you're replacing columns. Yeah. So to get Y, you take the determinant matrix and you put the constants P and Q into the Y column. Now you want to write it this way and not write over AD minus BC because you want to see where the things come from, not just formula. If you're having trouble remembering your formulas, there's a couple of reasons for that. Number one, you don't know what you're doing. That's why you're relying on the formula and you don't know where the formula comes from. So if you're relying on the formula to remember a formula and you're struggling to remember that formula, two reasons. Number one, you don't know the formula or what's going behind it. Or number two, the formula itself is bad. I'm thinking specifically of the quadratic formula. The quadratic formula is trash because it ignores all the geometry that goes into solving a quadratic equation and how important that might be. So if you ever have trouble remembering the quadratic formula, that's not on you. The quadratic formula itself is trash. Now, if you have trouble remembering something like the slope formula, like if you have notes for your algebra class and you're writing down the slope formula to bring in your notes, Now the problem is you. If you need to write down the slope formula, you don't know what the slope is for, and therefore you shouldn't be using that formula. Does that make sense? It's a tool that you're not trained on. You shouldn't be using it. It's a tool that you're not trained on, so you shouldn't be using it. Right now, there's a bunch of work going on at my house, lots of power tools being stored in my garage. I'm not trained to use those power tools, and even though it would have been really convenient the other day to just bust out that circular saw, I'm not trained in its use, and also it's not mine. So I am not going to mess with it because I would have ended up cutting off a finger. Do you know what I mean? Welding looks like a lot of fun, but I ain't doing it just because there's welding equipment available. I realize that that's how you learn, but there was no supervision as well. I got a lot of, I needed a smaller piece of wood. And I had a kind of a larger piece of wood. Oh man, just fire that up and zing, come right off. And so, and then the improvisation started. It's like, oh, well, I don't have a table or clamps to work with. And I go, oh, it's fine. Look, I got like a ladder over here and I'll just hold it. And that's when I'm like, oh, no, you're not a teenager anymore. If you cut off your thumb, it won't go back. So that's why I'm writing these things as determinants, because the determinant part, AD minus BC, that's not the hard part. So I don't need to write down what the formula is for that. I want to know where things come from. Because if I had just written PD minus BQ over AD minus BC, that would be easy to remember until you had to also remember AQ minus PC over AD minus BC. Now those two start to commingle and everything's all messed up. You don't know how to fix it because you don't know where things came from. And this is all side note anyway, because we're trying to Cramer's rule. But here's how Cramer's rule is effective. Damn it. I hate Cramer's rule. It's because Cramer's rule usually shows up in 3x3 determinants, and it's a waste of time to calculate a 3x3 determinant. It only applies to two equations and two unknowns that are going to have jacked up denominators like this one. So the denominators are 4 times 16 minus -3 times -3. So our denominators is 4 times 16 minus -3 times -3, which is the 55. Now, we wouldn't be writing this down, right? It's taking too much time already to write this down. The point of doing math is so you don't have to write down all the friggin' math all the time. But I'm just writing it down for illustrative purposes. Now, for the numerator on x, sometimes referred to as dx, that'll be the determinant where the 4 -3 column is replaced by a -1 column. So I go -16 minus a -3. And that's the -13. So x is -13 over 55. For dy, the numerator of the y, we would replace the y column. So I'd have 4 -3 for the x column and then -1 for the y column. Then I'll have 4 minus a 3, which is 1. And that's my numerator on the y. Shit, Cramer's rule is pretty fast. On a system of two equations and two unknowns. I will make a note that if you decide in some future situation to solve a system of equations using Cramer's rule, and you're writing these things down, that's what I would take off points for. The point of doing Cramer's rule is not having to write this down and just writing down the critical point. So the point of doing Cramer's rule will be write down the system and you'll be like, oh, here's my critical point. And if I'm like, oh, how'd you get that? If I perform an audit and say, how'd you get that? And you're like, oh, Cramer's rule. I'm like, oh, okay. Nice. But if you wrote shit down, I mean, oh, then why are you writing it down? What are you writing that down for? Because you should show your calculations, but they took place in your head. You don't draw what's in your head. You just write down the results. Anyway, so I apologize. This is my formal apology Cramer's rule. You are really good at 2x2 systems. It's just that at the time I want to talk about you, I'm talking about like 3x4 systems or 3x3 systems, like that. So you seem too much time to be too time consuming. Back to our original points. Second derivative test. Recall that we found the critical points by solving f prime equals 0, or in this case, fx equals 0 and fy equals 0, a system of equations. Some of you might note that this refers back to when we were talking about the gradients. We can also solve the vector equation, gradient of f equals 0. Notice that this is a vector equation. The gradient of f is a vector, and so the 0 has to be the 0 vector, so I put a line on top of it. If you don't put the line on top of the 0, I take off 1 billion points. But the plan was the same that we used before. First derivative, solve first derivative equals 0. Find out when the first derivative is equal to 0. Next, we want to classify our critical points. If you would recall, we had multiple ways of doing this. Number one, use the function and what you know about the graph of the function. Not sure where we are with doing about the graph of this function, but we'll talk about that in a second. Number two, see where the first derivative changed sign. A little more complicated to do that here because we've got two different derivatives. Number three, put your critical points into the second derivative to check the concavity. That's the plan that we want to go with, clearly, because of what I wrote at the top. The problem that we run into is that there are 4 second derivatives, 4 second partial derivatives. On color number 4. Well, this is what we want to talk about today. We want to check the critical points in the second derivative to classify the critical points as a local minimum, a local maximum, or neither a local minimum or a maximum. The problem is there are 4. The partial of fx with respect to x, which is going to be, let me put them all. Not quite. The partial of fx with respect to x, which will be 4. The partial fx with respect to y, which will be -3. The partial fy with respect to x, and the partial y with respect to y. Let's check our thinking, check our memory. Remember that when the second derivative at a critical point was positive, we would say that the function is concave up and we had a minimum. So recall, If we check the second derivative at a critical point and it came out positive, we concluded that the function is concave up at the critical point, and the critical point is a local minimum. Now down here in this situation, we got like kind of two of each, right? Fxx is 4, but fxy is -3. So when we look at fxx, this is just looking at the rate of change in the x direction and how that's changing in the x direction. So from our memory check, thinking about things being concave up, this indicates that in the x direction, it looks like our function is concave up at this point. Let's see what's going on in the y direction. In just the y direction, fyy, it looks like our derivative, our second derivative is positive. So it looks like we have a function that's concave up in the y direction. This suggests to us that there might be a local minimum at this critical point. In the x direction, we're making a concave up, and in the y direction, we're making a concave up. For those of you playing along at home, I'm doing this with my hands. X direction concave up, y direction concave up. I gave you the wrong perspective on that. Concave up in the x, and then concave up in the y. It looks like this is suggestive of this being a local minimum. Because with second derivative positive, concave up, local minimum, the problem is we've got these other two mixed partial derivatives. How can we take all this information and summarize it? Here's what we're going to do. We're going to put all 4 second partial derivatives together into one. I'm going to take fxx times fyy minus fxy squared. Don't write this down in pen. I'm about to erase it. Just this last term. This is what we're going to be thinking of. This last term, you might be thinking, what happened to this fyx? Why didn't I care about fyx? Because we got a copy. These are the mixed partials. For continuous functions, the second mixed partials will be equal. So really, we did use all 4. See, told you. No, it was squared. What we did was took fxx times fyy minus fxy minus fyx. But since the second mixed partials are the same, we can write that as fxy squared. Once again, we want to know where stuff comes from so we don't forget it. That's right. That's why we can square it, because fyx and fxy, the mixed second partials, are equal. So down here, we'll summarize this by saying fxy, we'll just pick one to represent and square it. Now, if you're thinking that this is very suspicious that this showed up right after I talked about Cramer's rule on 2x2 matrices, you are correct to be suspicious about that. I am about as subtle as a Marvel movie. And we did all this stuff with determinants, and you'll notice that the move that I used to calculate this d of xy, combining these four mixed second partials, was very determinant-like. fxx times fyy minus fxy times fyx. So this calculation here is the determinant of the Hessian matrix for the function f. That is definitely DVD bonus material. So when we're editing this, we're gonna cut that. We're not gonna leave it on the cutting room floor. It's gonna be in the DVD bonus material so we can sell you another copy of the movie later on. A little bit cynical, I guess. So this is the determinant of the Hessian matrix. It's just a way to organize the mixed second partials. fxx, fxy, fxz, fyx, fyy, fyz, fzx, fzy, fzz, and so on. Yep. It's called a pen check. See who takes notes in pens. Non-erasable pens. I try to come up with alternate scales for things. This is Leach's washing machine theory. Because we get, people get criticized for measuring things in washing machines, but it makes more sense. Measure things in washing machines and minivans. Those are valid units of measurement. A football field is a valid unit of measurement. Banana is a good one too, because you know, how big's a banana? And plus, if I said, oh yeah, this thing needs to be about 17 inches long, that doesn't really help that much. How many bananas is that though? You can look at a thing and figure out how many bananas should line up there, How many letter-sized pieces of paper, right? If something is 18 inches long, it's like this piece of the side of the paper and most of this side of the paper. We'll be off by one. Okay. Different scales. Like age for adults, the number is completely irrelevant. The number is stupid. How do people react when you fall? There's only 3 age categories. Number 1, they laugh at you. That means you're young. Number 2, they're like, oh my gosh, are you okay? That means you're probably like middle-aged. If they just immediately call for an ambulance, you're probably elderly. Now, they might, in addition, laugh at you, but the highest level 1, that's what determines your age group. So like in 20 years, I'll be up here, it's like, and so that's the Hessian matrix. Whoops, and I'll fall over. Now, that will be funny, and you should laugh at me, but I'll also be like 70 years old, so you should call ambulance, because elderly. That's an age scale that makes sense. What will people do if you fell over? If it's just laugh at you and then go about their business, you're probably pretty young. Yeah, probably. You see, the problem is that commercial, like everybody knows that commercial, I've fallen and I can't get up. It's like funny until your mom calls and she's like, oh, I've fallen and I can't get up. I'm like, oh, Mom, are you fucking with me right now? Or did you actually fall? It's like, oh no, I actually fell. Fuck. I thought you were going to be doing something funny. Well, yeah. When I got there, she was halfway up. Because she was like, oh, fuck, I'm going to die, man. And I'm pretty sure she was halfway up when she called. I'm just glad she had her phone with her. But I'm pretty sure she was determined, so I'm not calling him. I'm not calling him. And then she got halfway up, she's like, oh, fuck. Just get over here. No comments. So anyway. What are we talking about? Oh, yes. Confidence in math scale. Do you take notes in pen? Confident. Do you take notes in erasable pen? Less confident. Do you use pencil? Realistic. So in this case, if we calculate the determinant of the Hessian matrix at the critical points, this is why I kept going with this, because I knew that the second partials were all constants anyway, so I didn't have to evaluate at these points. So we're going to take the determinant of the Hessian matrix and evaluate that at the critical point, each of the critical points. We only have one, so it's not that hard. The determinant of the Hessian matrix is positive and fxx at this point is also positive. Therefore, we can conclude that we have a local minimum. Our critical point is going to represent a local minimum. It requires two things, not just the determinant of the Hessian matrix being positive, but also fxx to be positive. That's enough to conclude there's a local minimum. Two other conditions we need to worry about. One of them will tell us about a local maximum. If the determinant of the Hessian matrix is positive, and fxx is negative, then local maximum. If the determinant of the Hessian matrix is negative, then we conclude that's a saddle point. So here we have a list of all our possibilities. Or Julie. Did I miss anything? We could have the determinant of the Hessian matrix be neither positive nor negative. If the determinant of the Hessian matrix at the critical point is equal to 0, then the second derivative test provides no conclusion. Note that this does not mean you write inconclusive on your paper. I said classify it as a local maximum, a local minimum, or a saddle point. You have to say one of those three things. If the determinant of the Hessian matrix comes back 0, you have to do something else. So that's the important thing to note here. You don't get to just write inconclusive. Usually this means appeal to the graph. Just look at some values nearby. That will probably get you out of it. If I give you a problem and the second derivative test gives you the determinant of 0 from the Hessian matrix at the critical points, I have engineered that problem to do exactly that thing. So if you're like, oh, I just need to look around a little bit. I want to take a look at some points around. Maybe look at a graph. It's not going to be that exotic. Here's what I want you to think about. First of all, I want you to notice all the things that are going on. First, we check the determinant of the Hessian matrix. We're saying local maximum or local minimum if that value is positive. Then the only other thing that we check is fxx, whether fxx is negative or positive. So this, the D being positive means that the fxx will tell you the concavity. Essentially, we could use that fxx as our concavity test. But that only happens if this determinant of the Hessian matrix comes back positive. So first part, that comes back positive. Now I could just look at that 1 second partial derivative, fxx. So my question is, why do we not care about fyy? Why are we just checking on fxx? And that comes down also to this one. If D is negative, why don't I have to look at anything else? Why does that automatically tell me this is a saddle point? All right. So that's what I want you to think about. That's it for today. I will see you all on tomorrow. Everybody have a good day. And thanks for playing.